Okay, so now let us convert our one-dimensional code to a two-dimensional code. So to begin with, let us commit our changes that we had made for the one-dimensional code into a Git repository, so that in case if we make a mistake later on, we can recover our code and roll back the changes. So I'm adding few messages here to the one-dimensional code, what changes we had made. The next thing is to create a branch. First of all, add a tag, and let me name it one-dimensional code branching, so that we will be revisiting this branch at a later stage, so that we can convert our one-dimensional scalar code to a one-dimensional code for system of equations. Yeah, so once the branching is done, now we are ready to continue with the master branch, so that we can go ahead with the two-dimensional. First of all, I'll add some variables in the config file so that it is now suitable for working with two-dimensional mesh. We have advection velocity x and advection velocity y as well, instead of just a single advection velocity. And I think the this config file changes are done. The next thing is to make the cells two-dimensional. Now we have a two-dimensional mesh, so we will have number of x cells plus 2 times the number of ghost cells in one direction, and similarly in the y direction as well. And now we also have to define dx and dy in addition. And also we have a two-dimensional mesh, so let us initialize it accordingly. Also, our cell will be modified to have cx and cy and dx and dy, because it's a two-dimensional, so we'll have delta x and delta y as well. And the centroid will be defined by cx and cy. So I'm kind of using the same code here, just changing dx and dx to dy and cx to cy. That's it. So almost no changes at all. Now let us initialize our mesh, so that it now initializes a two-dimensional mesh, and we will initialize it such that there will be a square within the domain, such that the centroid of the cell, if it is between minus 0.25 and plus 0.25, then we will make the cell equal to, the cell value equal to 1, and otherwise it's going to be equal to 0. Now I'll just make sure that the right solution file functionality is implemented properly, because now it's a two-dimensional mesh that we need to write into the file. So now we should be able to check whether the initialization is done properly or not. Okay, looks like the file has been written properly. I'll modify also the Python code such that it is able to now plot a two-dimensional contour plot showing the two-dimensional distribution of the scalar field. Now I'm going to reshape X to make it two-dimensional. Similarly Y and U. And instead of plot function I'll be using contour F so that we can plot a two-dimensional distribution of U. And looks like that's it. Okay, the initialization is being done properly, so let's move on. So now I will start modifying one function at a time. So let's start with the time step calculator. Here in this case we have dt1 and dt2, and we can either take the minimum of dt1 or dt2. This is okay approach that we can follow, but a much better approach is to use the inverse of dt1 and inverse of dt2 to calculate the time step. Okay, now let us modify the boundary conditions by changing the update ghost cells. Here again we are going to add another for loop. So as you can see, I have added a for loop to traverse in the J direction, that is the Y direction, and I'll do the same thing again for the bottom and top cells. Okay, so the next part is to modify the variable reconstruction. So to do that, since it's a two-dimensional mesh, we will have east, west, north and south values, and not only just east and west values. Now we have to set up all these 4 values when we do the reconstruction. And the way in which we are going to do the reconstruction is just by doing 2 separate reconstructions, one in the x direction and one in the y direction, and we'll be using the same one-dimensional reconstruction functions, the ones which we have used earlier. So let us just start with the first order as of now. We will look into the other higher order methods in a little while, but just for testing purposes, let us only set up the first order, and I'll comment out everything else as of now. Now let me modify the calculate flux. Here when calculating flux, we have 4 faces now: the left face, right face, top face and the bottom face. So to do that, we will first traverse through all the vertical edges, and then we will be traversing through all the horizontal edges. Now traversing through vertical edges is very identical to what we have done in case of 1D, but now the vertical faces are going to also we have lot more vertical faces. For every row in our mesh, we have a set of vertical faces, so we need to traverse through all the rows one at a time, and that is why this additional for loop is coming in here. And other than that, the vertical faces is going to remain identical to what we have done in case of 1D. In addition, we also have to now calculate the flux for horizontal faces, and to do that, I'll just copy this for loop, and I'll just copy these loops, and I'll now apply it for the horizontal edges as well. If you look at the general trend as to what I am doing here, is I am mostly adding one additional for loop and doing the same thing as I have done for 1D in the other direction as well. So now let us modify the time integration. I'll again add one for loop here for the second direction, that is J. We have a two-dimensional mesh, so I have to change cell I into cell IJ, and instead of only dx, we will have a cell area now. Yeah, that's the change that I'm making now, and I'll just replace dx by the area. So again, I'm adding one additional for loop here to traverse in the second direction, modifying these cells to make it 2D, and yep, and I'll do it again for the case 3, that is 3-step RK method as well. As you can see, it's mostly copy paste and just adding of those additional for loops. Now similarly, copying to the 0th RK step, here it's just about adding one additional for loop, nested for loop to cover the complete domain, and we are done. So let's now run this and see whether our results are, whether we are getting any results, and it looks like we have done some error. There is some mistake in the code, so let's start debugging. So I'm just checking out whether the dt is being calculated properly or not. It looks alright. So also let us look that the time is being incremented properly. Well, that looks alright as well. And dx, yes, that looks alright as well. And then at this time I calculated it on a handheld calculator just to see that everything looks fine, that the dt is being calculated properly, and it seemed alright. So this is fine. So there must be an error at some other place. Okay, next I am investigating the ghost cell updater, and looking at this code, it seemed alright. I'm just now modifying delta x delta y. Okay, changing the cells did not give any out of array bound errors, so that only means that I have not interchanged cells x and cell y anywhere. So that's all that I was checking here. There was no problem here, I guess. Now the most important part when debugging a code is to stay calm and cool and look at one step at a time, just evaluating that your code is correct at every step. It's very important to stay cool and calm, because it might be just a very minor mistake somewhere and you might be overlooking it. So just check every step that everything is fine or not. So I was not able to fix this error for quite a long time, and then it struck me, oh yeah, at this point of time I realized, I think that it is nothing to do with the time step, but the problem was something to do with the flux calculation. And here I realized that there was a mistake. So this had to be multiplied by dy, and the other part of it has to be multiplied by dx. That is, the vertical cells have to be multiplied by dy and the horizontal cells have to be multiplied by dx. The horizontal faces have to be multiplied by dx. That was the mistake that I was doing, and I think I rectified it right over here, and now everything should work fine. Yep, looks fine at this point. If I use number of arc steps as 2, and if I use number of arc steps as 3 also, I think it worked fine. Looks fine at this point of time. Now it's time to increase the order of accuracy, starting with beam and warming method, and I've just copy pasted that particular piece of code, making it 2-dimensional, and now I have to set up all 4 sides: U west, U east, U north, and U south. So let's do it. So here again I am adding a 2-dimensional derivative here. Once I calculate du by dx and du by dy, now I can simply change, I can just move in that particular direction. U south is going to be the u value minus du by dy into delta y by 2, and similarly north is going to be and you see that there are some oscillations, as they are all expected in case of beam warming. This is not the limited beam warming. We have the jump, and therefore it's going to have oscillations. Now let's look at Lex-Van method. As we know from the one-dimensional case, the one-dimensional Lex-Van method is going to be even more oscillatory compared to the beam and warming method. So anyways, let's just check it out. So instead of backward differencing, I'm now doing forward differencing here, and there's no more change. That's it, and Lex-Van method is done. Let us also write code for the from method, wherein we will be doing a central differencing instead of backward difference or forward difference. So there are a lot of oscillations, but it does not blow up, and from method there will be lesser number of oscillations and it does not blow up. However, we are not using any limiter, and therefore we see those oscillations. So let's now implement the limiter and limited Lex-Van. Now instead of single ratio, we will have ratio in x direction and ratio in y direction. So let's implement it. And we will also have the limiter in x direction and limiter in y direction, that is phi x and phi y. And we get limited Lex-Van method, and yep, that's it. So this should not give us any oscillations at all, but there are few oscillations. That means there is some problem in the implementation, because the limited Lex-Van method should not give any oscillations at all. And this is just the debugging process. I'm just trying to visualize as to how much oscillation am I getting. So just trying to figure it out. And this is the Python code that I'm editing to make sure that I'm plotting the color bar as well. So here I have the color bar, and I can see there are minor oscillations. It goes up to 1 into 10 raised to 1.05 or so. I want to get rid of those oscillations. So to get rid of these oscillations, I have just reduced the epsilon value there, and I see that the oscillations have reduced. Let us get rid of that epsilon. And now we can see that the oscillations have totally gone away. Now finally let's do the error calculation. This will be required for doing an order of accuracy analysis. Let's just calculate the error, which is the exact solution minus the calculated solution. The exact solution is taken same as the initial solution, and that is it is being assumed that the the function is going to make one complete round and come back to its original place, and therefore the original function is same as the final function, and if it's not, then there is an error. As we can see here, the first order method, and visually we can see here that the first order method is much more diffusive compared to the second order methods. As we can see, it's much better than the first order method because this is the second order method. Finally, let's write the code for WENO. So again, we have to do reconstruction in the x direction as well as in the y direction. So I'm adding an additional for loop here. And you can see that there are a few oscillations, and it is expected from WENO method because WENO method is not prone to be TVD. So there we have it. Our code for two-dimensional mesh has been completed. It's very simple to parallelize the code in Java. I have to just use in-stream range, and I have to call parallel on it. On my laptop I have two processes, so it's utilizing both those processes, and that causes it to run in half the amount of time. Finally, let me also implement this SWLS method for a two-dimensional mesh. So I'll do the calculation of weights in x direction as well as the y direction, and it's a two-dimensional mesh now, so I have to do the reconstruction for all the meshes in 2D. So there it goes. Now let's have a look at the results that we have obtained. We can see that the first order method gives the most diffused solutions, followed by the second order methods, and the fifth order WENO is the least diffusive method. However, even though we can visually see that the WENO is more accurate or the higher order methods are more accurate, to be sure that nothing is wrong in our code, we have to carry out an order of accuracy analysis, and that is going to be the topic of the next video. So I'll see you in the next video. Until then, bye bye.